I'm Professor Sid Morris, the author of the online book Topology Without Tears, which is freely available at www.topologywithouttears.net. This is the fourth in a series of videos on writing proofs in mathematics, and it supplements my book Topology Without Tears. There are links to this book and to all these videos from www.topologywithouttears.net. One of the most important parts of pure mathematics is writing proofs. Writing proofs is not always easy. This is because some statements are indeed easy to prove and other statements are hard to prove. This video, or rather this series of videos, aims to help make it easy for you to write easy proofs. However, only with practice will you find it easy to write easy proofs. And in my book, Topology Without Tears, there is a large number of exercises for you to practice on. In the previous 3 videos in this series, you have seen that it is easy to start a proof. And I have emphasized that the word proof has a special meaning in mathematics, different from that in everyday use and different from that in science. The first thing we learnt is that before writing a proof, we have to be very careful to understand our starting point. That is, understand what information we are given. Our proofs must be watertight arguments. We learnt a proof should start with the facts that we are given. A proof should end with what we are required to prove. In between these two, there should be a series of sentences, each with a subject and a verb. A proof consists of sentences, starting with what we're given and ending with what we are trying to prove. Each sentence in a proof follows from the preceding one by logical deduction using what we are given or have already deduced, or using lemmas, propositions and theorems that have already been proved from the axioms. We learnt that the steps in writing a proof are: step 1, write down what we are given. Step 2, write down the definition of each technical term in what we are given. Step 3, write down what we are required to prove. Step 4, write down the definition of each technical term in what we are required to prove. So these steps are quite easy. So starting a proof is easy. Step 5 is to think. In this video, we focus on a method of proof called proof by mathematical induction. The idea of proof by mathematical induction can be thought of as follows. Assume that we are asked to climb an infinite ladder to a finite but arbitrary height. The first thing we would have to do is step onto the ladder. The second thing we would like to do is show that from wherever we are on the ladder, whichever step, we can always climb to the step above it. In other words, we have to step onto the ladder. We might call this the base case, the starting point. Then we need to show the inductive step, that we can climb from step n to step n plus 1. The so-called principle of mathematical induction then tells us that if we know the base case, or we can prove the base case, and we can prove the inductive step, then we can reach any step on the ladder. But how do we know the principle of mathematical induction is true? A simple answer is that it is one of the piano axioms for the natural numbers. We might then ask, how do the piano axioms for the natural numbers, which date back to the beginning of the 20th century, fit in with the Zermelo-Fraenkel axioms for set theory discussed in detail in my videos 2a, 2b and 2c on infinite set theory? That is a good question, but time prohibits a serious discussion of it here. Suffice it to say that the key figures in this understanding were Giuseppe Peano, Richard Dedekind and Bertrand Russell.
We recall that the set n of natural numbers is the set consisting of 1, 2, 3, 4, up to n, and so on. So the set n, as we just said, can be defined as a set which satisfies the piano axioms. Here I will mention only one of the piano axioms, namely the axiom of induction. The axiom of induction says, if S is a set of natural numbers such that 1 is in S, and whenever the number n is in S, the number n plus 1 is also in S, then the set S must be all of the set n of natural numbers. So that is the axiom of induction which we are assuming is true for the set of natural numbers, and we assume it is so because it is one of the piano axioms. The axiom of induction turns out to have many applications within mathematics, and also, in particular, many applications within topology. However, sometimes one needs a slightly different form of the axiom of induction. Instead of starting at the number 1, sometimes we start at some number bigger than 1. It's really a simple exercise to derive from the axiom of induction this slightly more general form expressed in proposition 1. So the more general form says, let S prime be a subset of the set of natural numbers, such that some number m is in S prime, and whenever n is in S prime, n plus 1 is in S prime. Then S prime must contain all of the natural numbers which are greater than or equal to the number m. How do we prove it? Well, we're given S prime. Let us define the set S to be S prime union 1, 2, 3, all the way up to m minus 1. It is now clear that this set S we've just defined satisfies condition 1 and condition 2 of the axiom of induction, and so the set S is equal to n. But S prime was all of S except the numbers 1 up to m minus 1. So S prime must contain the set of natural numbers minus 1, 2 up to m minus 1, which is what we're required to prove. So this version of the axiom of induction simply has the number 1 replaced by the number m. And that will often be the version we wish to apply. So we now have the axiom of induction, which we will express in a slightly different form when we proceed to use it. So without delay, let us see an example of how induction can be used as a method of proof. We begin with an example which does not come from topology, but nevertheless is quite instructive. Our example asks us to prove that n factorial is greater than 2 to the n plus 500 for n, any natural number greater than or equal to 6. We begin by recalling proposition 1. We shall use this proposition in our proof. So we are required to prove that n factorial is greater than 2 to the n plus 500 for n, a natural number greater than or equal to 6. We let Pn be the proposition n factorial greater than 2 to the n plus 500. And we are required to prove that Pn is true for all n greater than or equal to 6. We let S prime be the set of natural numbers n such that Pn is true. By proposition 1 above, if we can prove that, firstly, 6 is in S prime, so 6 is our m, and secondly, n belongs to S prime implies n plus 1 belongs to S prime, then proposition 1 will tell us n belongs to S prime for all n greater than or equal to 6. In other words, if we show that, firstly, P6 is true, and secondly, for n greater than or equal to 6, Pn true implies Pn plus 1 is true, then Pn is true for all n greater than or equal to 6. And this would complete the proof of statement 1 and hence prove the result. First, we must prove the base case or the initial case. That is, we must prove that P6 is true. What is P6? P6 is the proposition that 6 factorial is greater than 2 to the 6 plus 500. So let us look at the left-hand side. The left-hand side equals 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1, which is 720. Now let us look at the right-hand side. It's 2 to the 6 plus 500. That is 64 plus 500, which is 564. Of course, 720 is bigger than 564, so our proposition P6 is indeed true. So we have proved that P6 is true. Now let us assume that Pn is true for some n in the natural numbers, n greater than or equal to 6. That is, assume that n factorial is greater than 2 to the n plus 500 for some natural number n greater than or equal to 6. We are required to show, with the above assumption, that Pn plus 1 is true. That is, we are required to show, with the above assumption, that n plus 1 factorial is greater than 2 to the n plus 1 plus 500. The left-hand side of this proposition is n plus 1 factorial, which equals n plus 1 times n factorial, which is greater than n plus 1 times 2 to the n plus 500 by the inductive assumption that n factorial is bigger than 2 to the n plus 500. So for n greater than or equal to 6, the left-hand side is greater than, we just do this n plus 1 times 2 to the n plus 500, multiply that out. So the left-hand side is greater than n times 2 to the n plus 500n plus 2 to the n plus 500. Just dropping a couple of those terms that we don't need. This means it is greater than n times 2 to the n plus 500. N is actually greater than or equal to 6, so it's certainly greater than or equal to 2, so it's bigger than 2 times 2 to the n plus 500, which is 2 to the n plus 1 plus 500. So we have that the left-hand side is greater than the right-hand side. That is, 2 above is true. Thus, Pn is true for all n greater than or equal to 6. So this completes the proof of that example. So we began with the axiom of induction. It was a statement about the natural numbers. The axiom of induction said that if S is a set of natural numbers such that 1 is in S, and if n is in S, then n plus 1 is in S, then S has to be all of n. This can now be expressed in the useful form of the principle of mathematical induction. And it is this principle that we shall apply in all of our examples. What it says is, let m be a natural number, and for each n belonging to n, let P of n be a proposition. If P of m is true, and for n greater than or equal to m, Pn true implies Pn plus 1 is true, then P of n is true for all n greater than or equal to m. So this is the principle of mathematical induction, and it is the form in which we shall use mathematical induction in all of our examples in the future. No doubt you have seen this principle before, perhaps even at high school, but I hope now you can see that it follows from a very explicit statement about the natural numbers. It's not an airy-fairy logical result. It is a property of the natural numbers, the axiom of induction, which we have expressed in a useful form, which is the principle of mathematical induction. So let us move on to our next example. We begin by recalling our definition of a topology, definition 1.1.1 in the book Topology Without Tears. And I draw your attention to part 3 of that definition, which says that the intersection of any two sets in Tor belongs to Tor. Our example asks us to prove that if Tor is a topology on a set X, then every finite intersection of sets in Tor is a member of Tor. In other words, the intersection of 3 sets in Tor is in Tor, the intersection of 4 sets in Tor is in Tor, and so on. Not the intersection of an infinite number, but the intersection of every finite number of sets in Tor. So we need to prove that a finite intersection of sets is a member of Tor using the fact that we are given that the intersection of any two sets in Tor belongs to Tor. We begin our proof as we begin all proofs. We write down clearly what we are given. We make sure we understand each technical term in what we are given. We write down what we are required to prove. We make sure we understand the technical terms in what we are required to prove. And then we think about how to proceed with the rest of the proof. So we are given that Tor is a topology on the set X. That is, it satisfies definition 1.1.1 above. In particular, it satisfies part 3 of definition 1.1.1, that is, the intersection of any two members of Tor is a member of Tor. We are required to prove that each finite intersection of members of Tor is a member of Tor. And we shall use the principle of mathematical induction to do so. At the top of the page, you see a restatement of the principle of mathematical induction. You see that we need to define a proposition Pn, prove that Pn is true for the base case, M, and that if Pn is true for some n, then Pn plus 1 is true. And the principle of mathematical induction then tells us that Pn is true for all n greater than or equal to m. So in this problem, for each n belonging to n, let Pn be the proposition that each intersection of n members of Tor is a member of Tor. That is, Pn is the statement or the proposition. O1 up to On in Tor implies the intersection from I equals 1 to n of Oi is also in Tor. The first thing we have to do in a problem using the principle of mathematical induction is to check the base case. In this case, the base case is P of 2. Now, P of 2 says O1 and O2 are in Tor, implies O1 intersect O2 is in Tor. Clearly, this is indeed true by the definition of Tor being a topology. So P2 is true. Next, we assume that Pn is true for some n. That is, O1, O2, all the way up to On in Tor implies the intersection from I equals 1 to n of Oi is also in Tor. We're required to prove Pn plus 1 is true. That is, O1, O2 up to On plus 1 in Tor implies the intersection from I equals 1 to n plus 1 of OI belongs to Tor. But the intersection from I equals 1 to n plus 1 of OI is in fact the intersection of the first n terms with the last term. In other words, it's the intersection I equals 1 to n of OI intersect On plus 1. But our inductive assumption, that is what we assumed, was that the intersection from I equals 1 to n of OI is in Tor. But Tor is a topology, and so if we know the intersection from I equals 1 to n OI is in Tor, and On plus 1 is in Tor, then the intersection of those two sets must also be in Tor. But the intersection of those two sets is the intersection from I equals 1 to n plus 1 of OI. Thus we have Pn plus 1 is true. So we have shown if we assume Pn is true, then Pn plus 1 is true. By the principle of mathematical induction, then Pn is true for all n greater than or equal to 2, which completes the proof. Our third and final example on the use of mathematical induction assumes that you have studied the topic finite products in Chapter 8 of my book Topology Without Tears. However, even if you have not studied this far in the book yet, this example should still be able to be read with some benefit. So let's start the example. Let P be any property of a topological space such that whenever topological spaces X tor 1 and Y tor 2 have property P, then the product space X tor 1 cross Y tor 2 has property P. We have met myriads of properties which have property P. For example, the discrete space. The product of two discrete spaces is a discrete space. Indiscrete spaces, T0 spaces, Hausdorff spaces, metrizable spaces, compact spaces, and so on. We are asked to prove by mathematical induction that if the topological spaces x1 tor 1 up to xn tor n have property P, then the product space x1 tor 1 up to xn tor n has property P. In other words, if we assume that we have a property such the product of two spaces with this property has the property, then we get any finite product of spaces with this property has the property. So we're going to use induction to prove this, and once we have proved it, we have really proved it for discrete spaces, indiscrete spaces, compact spaces, metrizable spaces, and so on. So we don't have to do the same exercise many times over. So we begin the proof in the usual way. We write down carefully what we are given. We are given that the spaces x1 tor 1 up to xn tor n have property P. We make sure we understand what property P is. It is that if two spaces have property P, then their product has property P. Then we write down what we are required to prove. We are required to prove if the topological spaces x1 tor 1 up to xn tor n have property P, then the product space x1 tor 1 times x2 tor 2 up to xn tor n has property P. Now we are going to use the principle of mathematical induction, so we let Pn be the proposition that if the topological spaces x1 tor 1 up to xn tor n have property P, then the product space x1 tor 1 times x2 tor 2 up to xn tor n has property P. And we have to show that Pn is true. Then we need the base case. Our base case will be P of 2, and P of 2 simply says if we have two topological spaces with property P, then their product has property P. That in fact is immediate from the very definition of property P. So P2 is true. The next step in an induction proof is to assume that Pn is true for some n in n, and prove that this implies that Pn plus 1 is true. Now what is Pn plus 1? It's the proposition that if the topological spaces x1 tor 1 up to xn plus 1 tor n plus 1 each have property P, then the product space x1 tor 1 times x2 tor 2 up to xn plus 1 tor n plus 1 also has property P. So assuming Pn is true, we have to prove Pn plus 1 is true. But what is the product x1 tor 1 cross x2 tor 2 all the way up to xn plus 1 tor n plus 1? It's a product of two terms, where the first term is the product of the first n spaces, and the second term is the n plus 1 space. So in other words, that product of n plus 1 topological spaces is the product of x1 tor 1 up to xn tor n times xn plus 1 tor n plus 1. So we now have expressed this product of n plus 1 spaces as the product of two spaces. By our inductive assumption that product of n spaces x1 tor 1 up to xn tor n has property P. So we have that the product of the n spaces x1 tor 1 up to xn tor n has property P. We also know that xn plus 1 tor n plus 1 has property P. So we now have this product of n plus 1 spaces homeomorphic to a product of two spaces, each with property P. But by the definition of property P, the product of the two spaces x1 tor 1 up to xn tor n and xn plus 1 tor n plus 1 has property P. So we have the product of these n plus 1 spaces is homeomorphic to a space with property P. So the product x1 tor 1 up to xn plus 1 tor n plus 1 has property P. So Pn plus 1 is true. We have shown then that P2 is true, and that if we assume Pn is true, we get that Pn plus 1 is true. So by the principle of mathematical induction, Pn is true for all n greater than or equal to 2. That is, x1 tor 1 cross x2 tor 2 cross xn tor n has property P for all n greater than or equal to 2. You might ask why I added this n greater than or equal to 2. What if n equals 1? If n equals 1, the result is obvious. It is simply saying x1 tor 1 has property P implies x1 tor 1 has property P. So we now have completed the proof using mathematical induction. So let us summarize the principle of mathematical induction as it is used in our problems. When we're given a problem to be solved using mathematical induction, we first of all state very clearly what the proposition P of n we are trying to prove is. Having done that, we decide on the base case. That's where we start proving the induction. We call this case M, say, n equals m. We prove that P of m is true. Then we assume that Pn is true for some n, and using that inductive assumption, prove that Pn plus 1 is true. If we can do that, then the principle of mathematical induction says that P of n is true for all n greater than or equal to m.
I hope that you now have an understanding of mathematical induction and how a proof by mathematical induction should be presented to the reader. Thank you.